Pre-calculus notes 3.2, day 2. So we're going to work on graphing logarithmic functions, and we're going to use the fact that they are inverses of exponentials, meaning they are reflections in the line y equals x of each other. And so in the same coordinate plane, sketch the graph of each function. And so what we are showing here, we have the exponential 4 to the x. Here we have the logarithmic of the same base. These are inverse functions and the reflections over the line y equals x. And what happens is when you reflect in the line y equals x, the ordered pairs switch positions. And so on this one, when I say sketch these, I'm not picking up a graphing calculator. I'm going to just -2, -1, 0, 1, and 2. I'm going to use 4 to the x. It's going to be 1 over, well, it's 4 to the -2, which is 1 over 4 squared, or 1/16. 4 to the -1 is 1/4. 4 to the 0th is 1. 4 to the 1st is 4, and 4 squared is 16. So it's kind of hard to graph to 1/16, but -1, it's 1/4. At 0, it's at 1, and at 1, it's at 4, and then it's off the chart. So here I have the function y is equal to 4 to the x, and you should show it goes off the chart between 1 and 2. And so there is your y equaling 4 to the x. Or since it was f of x, we could just label it with f. And so that, I think, is the easiest way to get your points on the logarithmic function, because the logarithmic functions are reflections of the line y equals x, and so all these ordered pairs just switch. However, if you are, thinking about putting in values and choosing them, it's better if you choose arguments that are powers of 4, because 4 to what power is 4? 1. 4 to what power is 16? 2. 4 to what power is 1? 0. And then 4 to what power is 1/4? Well, that would be a -1. 4 to what power is 1/16? -2. And that's really what's happening on those. And then the line y equals x has a slope of 1. And so when I reflect these points, the ordered pair changes. So instead of being at 0, 1, you're at 1, 0. Instead of being at 1, 4, you are at 4, 1. And then you'd be off the grid that way. And instead of having a horizontal asymptote, you have a vertical asymptote on exponentials. And so at 1/16, you're at -2. And at x being 1/4, you're at -1. And so this function follows the y-axis, getting closer and closer as it goes on down. And then it goes off between the height of 1 and 2, that direction. And this is your g, which is your log base 4 of x. So that is the best way to, without picking up a calculator to do it, to graph the log, is to first graph the exponential, that is its inverse function, and then switch those ordered pairs to get the basic parent function for log base 4 of x. So in example 2, when it says sketch the graph of log base 3 of x, then what I am going to do is think about y is equal to 3 to the x. And then switch the ordered pairs to get the basic log base 3 of x. So for y equals 3 to the x, I have a 1/9, a 1/3, a 1, a 3, and a 9. So that means the basic parent function for log base 3 of x is to switch these. 1/9 is a -2, 1/3 is -1, 1 is 0, 3 is 1, and 9 is 2. So now what we're doing to this parent function is we are doing transformations. And it said, first of all, sketch the graph of this logarithmic function. Sketch the graph of f of x is equal to log base 3 of x. And so at 1/9, we're at -2. At 1/3, we're at -1. At 1, we're at 0. At 3, we're at 1. And at 9, we are up at 2. And so there is the sketch. This is your y equals log base 3 of x. So now this right here, the transformation is you are just going down 3 units for your parent graph. And so you should show, table of values on that. And so for going down 3, I am going to subtract 3 from the y's. So the x values are not going to change. It is just the y's. So I've got my basic table for the parent function of log base 3 of x, and now the y values are just going to go down 3 units. So down at -5, down at -4, down at -3, and then at -2, and then at -1. So we've got at 1/9, we're at -5, and at 1/3, we're at -4. At 1, we're at -3, and at 3, we're at -2. And that means we have dropped, just every point down 3 units. That's all that we're doing. And so we'd be down, I'm off a little bit there, right there. So there is y equaling log base 3 of x minus 3. Just drop everything down. So it just drops everything down. Versus now on this next one, this makes everything go left 2. And so now we're going to have a vertical asymptote at x equals -2 instead of x equals 0, the y-axis. And that affects your x coordinates, not your y. So right here, if I have log base 3 of x plus 2, my parent function values are going to be the same for the y's, but I have to subtract 2, and 1/9 minus 2 is a -1 and 8/9. And 1/3 minus 2 is a -1 and 2/3. And 1 minus 2 is a -1. 3 minus 2 is 1. And 9 minus 2 is 7. So at -1 and 8/9, I'm going to be at -2. -1 and 2/3, I'm at -1. -1, I'm at 0. And at 1, I'm at 1. So every point shifted to the left 2. And then at 7, I am up at 2. A nice sketch going here. And so you need to be able to work out tables of values. Notice I haven't picked up Desmos. I have just used transformations of functions in order to get those sketched accurately and to produce tables. Now let's look at some of the characteristics here. Well, since I'm in this code, this means that I have a vertical asymptote at x equals -2. I don't have the y-intercept because it's kind of something a little strange, so we're not going to worry about that on that one. For this function, log base 3 of x minus 2, you have a vertical asymptote of x equals 0. There is no y-intercept. The x-intercept, we're not going to worry about finding. It didn't come out in the graph. It's going to be further to the right. And then for this basic parent function, you have a vertical asymptote of x equals 0. and you have your x-intercept of 1, 0, or x equaling 1. All right, so then let's move on. That's good. Find the domain. And the key is that the argument must be greater than 0. So you can only use values of x that make those inputs, the argument, greater than 0. So right here, this is your argument. We can't take the natural log of a negative number. We saw that where if you put it in, you get an error message on the calculator. So the domain of this is x plus 5 has to be greater than 0. So x has to be greater than negative 5. So using interval notation, the domain is negative 5 to infinity. In part B, again, this argument has to be greater than 0. So 3 minus x has to be greater than 0. Be careful on this. 3 has to be greater than x, or x is less than 3 on this one. On this one, the negating of the x has that effect of reflecting over the y-axis, and so the graph ends up going to the left of the y-axis rather than to the right, so that x is less than 3 on a number line. You know, if this is 3, we're talking to the left. So in interval notation, I would write from negative infinity to 3, and the 3 is open. It can't actually be 3. And then f of x being x cubed, no matter what x is, it has to be greater than 0. Well, a negative value cubed would be negative, so I can't let x be negative. X can't be 0 because you can't take the natural log of 0. That's not in the domain. It has to be greater than 0. And so x cubed will be greater than 0 if x is greater than 0. And so that is my domain. So it is 0 to positive infinity. That's it.